notice that? Go ahead.
Displacement of plane normal to magnetic field increasing with time as B is equal to 1 T.
All right. I'm going to have the B field coming out. So the B field has a function of time that's coming out. And what's the equation of B field? Or it's the time derivative of that. They give you a time derivative of the B field? And what's the value? 1 per second. All right. Do your stuff. This is 1 Weber per meter squared per second. All right, that's fine. And they want the actual induced magnetic field? Or the induced voltage?
They want the induced current.
Is there a resistance or is it just a wire?
It's just the wire.
All right, here's how you do this kind of problem. And I want you to please pay attention here. These things can be a little tricky. And you don't have to write this part down, but I want you to hear me. So, these are classic problems. If we take this, I know we're gonna complete the circuit. But let's break this right here and call this plus and minus VEMF of P. Now, you remember when I talked about this last time? We start with curl of E is equal to minus dB dt, right? Y'all remember this? And then we integrated both sides, so I integrated curl of E dot ds over the surface, so it would be over the interior of that loop. And that was equal to minus d dt of the integral of the B field dot ds. Y'all remember me doing this? I'm being a little casual with some of this, but y'all remember this? How many do? Just show hands. All right. Now, this is really the flux that's flowing through here, isn't it? Right? So when you take a look at that, I have minus d dt of the integral of B dot ds. And I can do that really and say that's really, there's a minus sign. It's minus, and then I can do this. I can say it's the integral of dB dt dot ds, and I can take that derivative inside. Usually you leave it out because the integral of B dot ds is a magnetic flux. Usually leave it out. In this case, I'm going to put it inside for a reason. They tell me what the value is. You all see that, class? So that means when I look at this, the integral of curl of E dot ds is really the integral of E dot dl in the counterclockwise direction around the closed loop. And this is, by definition, the induced voltage as a function of time. Now, I did this last time. You all remember this? Let's come over here. That means this voltage as a function of time is really this surface integral of minus dB dt over the integration over the surface. You all with me? Now you can see the B field doesn't vary spatially. And they give us this derivative, right? And it's perpendicular. You all see this, class? It's coming out of the board. So the integral of dB dt dot ds is just that value 1 times the dimensions of the loop, because it's really a rectangle. You all with me? Or square. So that means this right here is going to be equal to minus, and that's just 1 time, so it's really 0.04 squared. Now that's the induced voltage. Do you all agree? Just think about that. It's 4 times 10 to the minus 2 squared, or it's what? 16 times 10 to the minus 4, and that would be volts, and this would be the voltage, but there is a minus sign here. Now I'm going to explain this. Just be attentive here. This is important. So, if I take a look at that, can you all see in the back there's a minus sign there? That's times 16 times 10 to the minus 4. Do you all agree with this? How many do? See. Back there, you guys see it? Okay. All right. Now, what does that really mean? Well, if I look around here, and I kind of sketch the induced electric field, this would be the induced electric field caused by the time-varying magnetic field. It means this is positive and this is negative, but if you look, this has a value of minus 16 times 10 to the minus 4. Do you all see that? So what I typically do, and what most people do, is I'm going to erase this. I know this would be minus, but I would like to see a positive potential. So I make this plus down here, and this minus, and this is going to have a value of 16 times 10 to the minus 4 volts. Does that make sense to everyone? Give me a show of hands if you see this. Now, you'll notice the polarity. The next step is critical. So if I short this thing out, I need to include a source that would cause any break in this wire to have a plus minus potential. Y'all follow me? So how would I do that? Well, if you look at this, I'm going to complete this circuit, but what I would do is this. I'm going to put a source in, and this source is going to have a voltage. Now think about it. We want to get the current going this way now, right? Because think about it. When there's a break, it has to accumulate positive charge. This would be negative. How many understand that? So what I do is make this plus here, make this minus, and just put the voltage there, which is 16 times 10 to the minus 4 volts. Now this looks like a source. A source right here, a voltage. Now, if I all of a sudden break the wire and look, you'll see the positive voltage would be here, the negative voltage would be there. Does everybody understand it? How many do right here? So now we complete the problem. Now I'm going to short that out. That wire has an internal inductance and it has a resistance. I think in Whitworth's book he's just worried about the resistance. I'm not certain about it. If you're only worried about the resistance, then the resistance of a wire, now this is constant cross-section all the way around. You all agree? So it's proportional to the length. Well, the length is really what? 4, 4, 4, 4, so it's what? 16 centimeters, correct, class? So the formula I'm using is L over sigma A. So L is going to be 16 times 10 to the minus 2. Is this copper wire?
Yeah.
All right, so for copper, the conductivity is 5.8 times 10 to the 7th. And the units would be Siemens per meter, but I'm going to just leave it like that. Y'all with me, class? You understand that? That's the conductivity, 1 over the resistivity. In physics, they use resistivity. Then it's times the area. And the area would be pi radius squared. What is the radius of that wire? 1 millimeter? Did you say 1?
Oh, it's 0.5.
The diameter 1 millimeter, is that it? All right, then divide that by 2. So it's going to be, well, we'll just do it this way. Since it's 1 millimeter, 10 to the minus 3rd, divide by 2 and square. You don't have to do it this way. You can just take, really what, 5 times 10 to the minus 4th and square. You all with me, class? Now, can somebody, if you have that resistance, I don't know what it is, but you can give that to me in a second. Once we have that, they want the current, right? So the current is going to flow in this direction, and the value of that current is going to be simply the induced voltage over the resistance. That induced voltage is 16 times 10 to the minus 4th. Can you tell me what that resistance is?
3.5 millions.
3.5 millions? So it's divided by 3.5 times 10 to the minus 3, and tell me what that is.
0.46 amps.
Is that right? In the solutions class? Now that's a classic problem. I mean, anything like this. I'm going to tell you that, well, first, any other questions before? How many tried the problems? All right, if you did the chapter 5 on this and on the prior section where we did really use current density to get charge density, you should be set for the quiz. I want to just mention a few other. Did you have a question? No, ask me. It's all right. If you can't read my writing, I'll try to interpret. Question or?
it's just, no, she was asking where the length came from for the resistance value.
Oh, I mean the formula you mean?
Or just how you got the numbers.
Well, the length is just a perimeter. It's so take a straight line, bend it into a square. It's the length of the straight line. Does everybody follow me on this one?
And there was the second part to this question.
Go ahead.
The field at the center of the loop from a single arm of the loop is found. What's the second thing?
It's calculate the magnetic flux density at the center of the loop.
It's given, right? The B field is given. I mean, maybe I missed something.
So once you find the H field, and then you
Find the flux from the
Just-
induced current.
The what?
The flux from the induced current.
Oh, the flux created by the currents?
From
Is
the
it?
induced current.
All right, now what he's saying, I think he's saying is that that current's flowing, there are four arms, right? They're all short dipoles. So if you want the magnetic flux in the center, is that it? Just listen to me on this. This is where engineers, good engineers, see through an easy solution. So what I'm going to do is this. I'm going to erase this, and since that's the right answer for the current, I'm going to go ahead and erase this. I'm going to say one thing. I'm going to make an argument, and I hope you understand this. If that's the direction of E field, the actual current is flowing in this direction too. It's going this way, the actual current. Y'all follow? Now, I want you to take a look at one thing before I continue. If you look at the direction of the H field or B field inside this loop, use the right hand rule, take your thumb, we're going to get it from each side. Put your thumb in the direction of current and your fingers on your right hand curl in the direction of the field. It's coming out from this one. You all see it's coming out on the board from the top? Yes, sir.
So in the book solutions, you have the current.
Well, I mean, the way I showed it, I don't know about your solutions, but sorry, I had a voltage like this. Sorry, I'm bad. This is wrong. It would be going this way. I'm not really worried about it. You follow me on this? All right, if it's going that way, then the field, magnetic field created by those wires is into the board. Do you all agree with that? I'm sorry about it. If that's the case, here's my argument. I'm going to say, if we look at just one element here with a current I, and I guess current's going the other direction here. Let's look at this one if it was short. And we have this loop here. You all agree? Now remember, that's a short dipole, right? I mean, it's a dipole that's not infinitely long. You all agree with this? So, if I find from this, if I find the H field, or maybe the B field here, and I mean, there's an equation for this, the B field here going into the board, and then integrate that B field over the surface area, just from this one. So I'm going to say, I'll call this member 1, right here. So if I take a look at the magnetic flux through this surface, just from that, it would be always, it's going in this direction. If you think about it, if the current's going this way, the flux from the one going up here is in the same direction as the flux, the one here, and the flux, I mean the H field or B field from the top one is in the same direction as the bottom one. Do you all see this, class? In other words, they're all additive in a positive sense. You agree, class? Now, if that's the case, here's my contention. If I find just the magnetic flux going through this 4 by 4 centimeter area from one element, one link of the wire, I can multiply that 4 by 4 and get the total. Does that make sense to everybody? So, really, I can say this is equal to the double integral of, I'll call it B1 dot ds. That's actually going in this direction. That would be, you know, we could do the thing. But then I'm going to multiply by 4. And when I do that, I get the total flux. And that would be the total flux flowing in that. Because the flux integration from each one of those elements will be the same. Do you all see that? Because they're identical amounts of current in the size. So from the one going vertical, if you find the B field from that, integrate it over that surface, you're going to get about from the top one, if you did the same thing, you're going to get the same value. So you just do it one time and multiply by 4. With me? Now, how do you find the flux from just one of these things? Does he say anything about the approximation or anything like that?
Once we find the flux density,
Flux density at the center?
yeah, so that's just B.
Just the B field then?
Yeah.
Oh, okay. So if he wants the B field at the center, you find the B field at the center from 1, you multiply by 4. That's it. I'm going to just finish this up and let you guys see this. Now, I don't know where it is in the book, but for a wire that's not infinite, this is, I want to make sure I say this correctly, but straight, and let's put it on the z-axis. You have to concern yourself with the radius of the wire too. This becomes, there's 2 facts. So if you look at this, oh, they just want it at the center. You don't actually. So if I have a wire here, and it's got a current I here, going up, and say this thing, I'm going to go right from the center here. This thing has a length L, and I want the flux here, right in the center. So I have rho here that's really L over 2, and I'm trying to draw this the way he probably does it. So I need the B field right there. Y'all follow me? I need the B field from this single wire that's on the z-axis, at length L. Has a length L, but basically I'm trying to show you just one member of it, say the one on the z-axis. Y'all with me, class? It's 4 centimeters long. I can put L is 4 centimeters, and that means this is going to be 2 centimeters away. Now, in the book, he'll have something for the H field, for this, and it will be I over 2 pi rho. If you can tell me where this is, let me know. And then, it's going to be, actually it's 4 pi rho in the book. Hold on. He's going to have it this way. A couple of ways you could do this. So it's this divided by 4 pi rho, and then it's going to be cosine of this angle and the cosine of this angle. You need to put, it'll be cosine of theta 1 plus cosine of theta 2. He may have had a sine instead. And that's going to be the actual H field right at the center. Y'all see this? What page is that on? I don't remember. I'll tell you a trick on memorize to remember this. You know? This would be in the beginning section and calculate the H field for a straight wire. He'll have the first limited just the length, and then he'll have the infinite. Anybody? Say again? Did somebody say it? It's in there somewhere. Here, this is in chapter 4. Maybe he doesn't. Does he have this formula in the book when he solves it or not?
There's a similar problem on page 300. That's ahead of where we are right now.
It's all right, but there's one.
The equation that he uses is on page 216, number 4.7.
All right, let's do it this way. 216, did you say? Let's take a quick look. Yeah, but that has infinite limits. You'd have to
He
change
set
it.
the limits on this problem from
You don't
negative
need to
A
do
to
that.
positive
I mean, you can do that, but that's with the cosine. All right, let's just see if this works. All right, so y'all agree that this This would be 2 from here to here. This is out 2, so this is 45 degrees. Does everybody agree with that, class? So if you do the math on this, we're going to get cosine of 45 degrees, which is 1 over square root of 2. Cosine of 45 degrees is 1 over square root of 2, correct? Right? So now you're going to get this. The H field at the center would be I, that we calculated, over 4 pi, and this is 2 centimeters would be a rho, or 2 times 10 to the minus 2 here. And then you have 1 over square root of 2 plus 1 over square root of 2 is 2 over the square root of 2. So you have now 2 times square root of 2 here. And that's the H field from one of them. I want to just finish this. Y'all with me? This is an easier formula. You can choose one. Now, if you get that, that's the H field. If you get the B field, you multiply that by mu naught, right? Isn't that right? H dot, what?
I think it's 2 root 2 out of 2 times.
Oh, sorry.
Sorry.
So this should be this. This should be 1 over square root of 2. So it's 2 over the square root of 2. My bad. There's 2 of this. 1 over square root of 2 plus 1 over square root of 2 is going to be 2 over the square root of 2. Y'all agree with this, class? All right, now if you have that, if I multiply by mu naught, now I get the B field, right? That's for 1. There are 4 members to that square root, right? So I multiply it by 4. And this would be the B field. Who wants the B field, right? Did you say? Or H? All right, this would be the B field at the center. And I'm going to just do this quickly. I can see that I got 4 here and 4 here I can cancel, right? Then I got 2 here, 2 here I can cancel. And let's see, then I have, what is this going to be? So this is going to be I mu naught, which is really 4 pi times 10 to the minus 7. It's that on top, and it's divided by pi, and it's square root of 2 times 10 to the minus 2. I forgot what I was. It was like 0.4 something, right? 0.46. Go ahead and run the math on that. Tell me what you get for the B field. Anybody have a calculator? Just give it a shot. And then I want to talk about that formula real quick. Okay? Just do this one. All the pi's can cancel. Sorry, might as well cancel the pi. So you got 4 times I times 10 minus 7 over square root of 2 times 10 minus 2. You get it? Anybody? Go ahead and say it.
0, 0, 0, 0, 7, 8. So 78 times 10 to the negative.
Say that again.
Or, yeah, okay, so 7.8 times 10 to the negative 3.
7.8 times 10 to the minus 3 Webers per meter squared. Is that what the book has? Anybody?
I got 13 micro Webers per meter squared.
All right. So 13 microwebers per meter squared. What answer is in the book? Honestly, it's just.
The answer is 13.
Negative 13 microwevers.
All right, the magnitude is 13 micro. You understand how I did this? I basically just find the H field from one element at the center. And I use this formula. And here's how you can tell this formula is right. All right, what if that wire is infinite? Think about it. And we're out 2 centimeters. What is this angle? If that wire is infinite, what's that angle? It's 0, right? What's the cosine of 0? What's this angle? 0 if the wire is infinitely long. Cosine of 1, or cosine of 0 plus cosine of 0, that's 1 plus 1 is 2. When this becomes 2, you can see it cancels. That 4 makes it a half, and you get the exact equation, I over 2 pi rho. Y'all follow me on that?
Where does this root 2 come from? The square root of 2.
What is the cosine of 45 degrees? It's what? 1 over square root of 2, right? There's 2 of those, so it's 1 over square root of 2 plus 1 over square root of 2. It's 2 over square root
Is
of 2.
that because it's a square?
Well, it's at the center. This is 45 degrees, this is 45 degrees. You see that? Now, if you had it down here, then this angle would be 90 degrees, right? And this angle would be reduced, I don't know.
I think what the book did is it took the equation for the infinite line and then
No.
modified it.
No, I didn't. It wasn't an infinite line. He did that. He put limits on the integration instead of going from minus infinity to plus infinity. It went from minus L over 2 to L over 2. He should, I don't think he has that in my book, but in that equation, you cite that is actually something where he goes from minus infinity to infinity. So it should go from minus L over 2 to plus L over 2. Y'all with me, class? That's an interesting problem. All right, other questions? Who asked that, by the way? You asked, does that answer your question? Anything else? By the way, these problems, most of the time, really boil down to your understanding of the induced voltage and direction of induced voltage. It's always the time rate change of the total flux through a loop times, I mean, it's basically that, but you have to put a negative sign to get the sense of the voltage. Now, I want to do one other problem, and I want to make sure you take a careful look at this. I'll put some additional problems up. Did I just put problems in the book, or did I post a few others that were not in the book? Just these? All right, I'm going to post some that aren't in the book that'll help you a lot, but I want to show you one, and then I'm going to talk about a few other things with time remaining. All right, so when you think about that problem, that was a very simple problem. Here's a more realistic problem. You do this in the EMC course. It's an actual real-world kind of problem. Suppose I have a resistor here. I'll call it 50 ohms. And I'm going to have a resistor here. And I'll call it 100 ohms. And then I'm going to have an open circuit here. And I want to know this voltage. That's what my goal is. I'm not done yet, but just follow me. Y'all with me, class? Now, if this has a dimension, I'll call this dimension H. And I'll call this dimension, you can make H anything. I'll call this L1, and I'll call this dimension L2. Everybody follow me on this? Now I'm going to put a B field, and I'm going to, or an H field, I'll put an H field. I'm going to say an H field comes out of the board here, and it's H of T. And I'm just going to say that H of T is, you've done this a lot with circuits problems. This is a bit fictitious, but if you look at this, I'm going to say H of T is going to be some H naught e to the j omega t. Now remember, that is kind of fictitious. The actual observable component would be the real component of that, which would be H naught times the cosine of omega t. Y'all follow me? Remember when you did circuits problems? He assumed everything was actually, I mean, for steady state circuits problems, it varied as e to the j omega t, right? But at the end of the day, when you solved it for time domain, you had to take the real part of the actual answer, right? You had to multiply by e to the j omega t. You had to take the real part to get the actual time domain form. Do you remember doing this, Dr. Roman's class? He doesn't usually make you do that second part. What he does, he just wants magnitude and angle for a voltage current, typically. Unfortunately, in the real world, it's time varying, so the observable, the real world that you would observe if you measured, will be time varying. So you have to multiply the answers you get by e to the j omega t, and then take the real part of that. And I'll go through this more with you. It probably rings bells. Yeah. I'm going to assume this is the case, and the field's coming out of the board. So let me try to do this for you. I'm going to have this is x, this is y, this is z. So it's coming out of the board. This would be ax. I think you all see this, right? Now, if you look at this problem, and I want this voltage, you have to see where closed paths are and where paths are not closed. You all see that there's a loop here that's got a closed path. All right? Current can flow in that loop. You all agree with that? no current's gonna flow here. Right? I will be zero flowing here. If you think about mesh analysis, y'all with me? No current's gonna flow in that second loop, but there is gonna be a source. So what typically you do is this. Draw the dimensions up. And I'm just gonna do this. I'm closing it already. And then what I'm going to do is this. I'm going to say, and this has a height h, and this has got L1, and this is L2. What I'm going to say in those two loops, that I've closed them, doesn't really matter at this point. I'm going to break the loops as such. I'm going to say what I have in this loop right here, I'm going to have a voltage source. I'm going to do it this way. I'm going to have some voltage source here, plus or minus, called V1, that I'll talk about in a second. Y'all with me? Because when you break this loop, there's going to be a voltage development. You can call V1 EMF if you want. And in this loop, right here, there's going to be a voltage. And I'm talking about this loop by itself and this loop, actually. Yeah, and this loop by itself. Now, if you think about this, and this gets a little, people sometimes get confused in this. If you take a look at this, and I want to know what this voltage is, right? Let's just isolate on that loop. If I, remember I have the H field defined everywhere. If I have, and I'm going to open it now. Actually, let me do it this way. I'm going to find the induced voltage right there. And I won't confuse you on this. Just for this loop right here, I'm going to find the induced voltage here, V, E, and F here. So it's this. I know the H field's coming out of the board, right? Now, if I want to find that voltage, as I've shown you, the induced voltage here as a function of time will be the integral, double integral of the B field dot ds, and I have to take a time derivative. I have to put a minus sign. I just showed you that earlier. Do you all remember this? So really what I'm getting is, since the B field doesn't change anywhere spatially, what I can do is take this, right here, take this itself, the V, E, N, F here, as a function of time will be minus, and there is a time derivative that I'm going to do in a second, B dot ds, well that would be mu 0 times my H field, H naught, times e to the j omega t, actually, let me write it over here because I'm running out of room. I'll get VEMF of t is going to be equal to minus d dt, right here. And then it's the integral of surface integral of mu 0 H naught e to the j omega t here, ax, and then dotted with, and this is going to be dz dy ax. Now, I'm trying to just show you form. This is formal. If you want to do. Y'all follow me? I'm just stating the integral with the actual value of the flux that I've chosen. The H. Yeah.
So we're going to dz dy matter?
No, it doesn't. As a matter of fact, you're going to see it's really just going to take the area times the H field in a second. Ax dot ax is going to be 1, right? Now when we take a look at this, mu 0 H naught e to the j omega t are constant spatially, right? They don't vary spatially. Take it out in front. So I get minus d dt of, and then I get mu 0 H 0 times e to the j omega t. And then that integral is just the surface. So it's really going to be L1 times H. Do you all agree with that? Now you do the time derivative, and what do you see? I mean, I'm just doing the integration because nothing very spatial, it's just the area of that loop times the h times the mu. You all follow me, class? Let me see this. Now you take the time derivative to get the actual value of VEMF. And you find it, and I'll do it here, VEMF for that first loop right here will be equal to minus, and the j omega comes out, minus j omega mu 0 h0. And I'll just use this symbol area. That's going to be L1 times h times the area. Now, does everybody follow me on how I did that? I took the time derivative of that. Time derivative of e to the j omega t is just j omega e to the j omega t. And I can leave the e to the j omega t in here, but you're going to see in a second how that. Y'all with me?
Is that L1H in front of the E?
Yeah, what I'm really saying is this loop right here. So it's L1 times h would be the area. Y'all follow me on this, class? I get to that. That's the voltage. You'll notice the negative sign. Can everybody follow me on this? So what I do now is I say this actual VEMF, I'm going to reverse the signs. And I'm going to say this is going to be positive and this minus. And the value of this voltage right there, the open circuit voltage, right here, I call it V open circuit, is just going to be J omega, going to be J omega mu 0 H naught times the area times e to the j omega t. Can everybody follow me on that? Now, what you can see is the voltage in each one of these loops is really just the area of the loop times the time derivative of the flux. Y'all follow me? Time derivative of the magnetic flux. And since that voltage is developed this way, if I was going to put a resistor here and still get that voltage, right? I have to have a source. And the source is actually this. It's going to be in the opposite direction. It's plus to minus, and my V source here will be equal to, if you look at it, I've got the polarities there, it's just going to be equal to J omega mu 0 H naught times the area times e to the j omega t. I'm going to put a source there, and then I can put the resistance in there. Now, if you look at that source, if I remove the resistance, it still develops the right voltage. Do y'all follow me? The polarity sense. How many see this right here? There's no current. All right, now getting back to this problem, here's what happens. Remember, the sense of that voltage is to cause current going counterclockwise. Y'all with, or clockwise, pardon, clockwise. You all see that? So what I can do is say over here, what I can really do, and I'm going to do it right here. This loop will have a voltage source. It'll be plus to minus, and the value of that source is going to be what I have there. Voltage here is J omega mu 0, and you might as well just put L1 times the height H. That's the voltage here, called V1, times I got the mu naught times e to the j omega t. And the voltage here, now, you'll notice how the sense of this is causing current in this direction, class? You with me, everyone? It'll be the same sense of, the same thing will happen in this second loop. It'll want to drive current clockwise. So the source over here, and I'm putting the source in, I can do it right like this. This source will be plus to minus, and it's still going to have, let me do it this way. This is still going to be V2 is just J omega mu 0, and it's going to be L times H times e to the j omega t. And then you have this. And I want this voltage. It would be it would be H times H times L2. Can you all follow me on this? Now, hear me on this one. This is the last point. Maybe it isn't. Yeah. Go ahead.
Like, are they,
Think about this. If you had two voltage sources, forget the magnetic field, and you wanted a voltage here, how would you do it? Anybody. That's basic circuits, isn't it, class? What do you do? Well, you know this, there's no current from this source because there's no what? There's no path, right? It can't flow back to the source, right? It can't flow this way because there's an open circuit here. This is the only path that is available. Do you all agree with that? How many see this? So if I wanted the current in this loop, or I wanted the voltage, the current in this loop, call it I1. I1 would simply be that voltage, V1 over, I'll call this R1 and R2. R1 plus R2. Do you agree with that? How many see it? Yeah. You got it? Did you have a question?
yeah, so the voltage is for the.
Class, I got what before I say. See, this class is going to be over in about 9 minutes, I think, right? How about we do the quiz Friday? All right, are you okay with that, everyone? I'm sorry, but I'm trying to finish this thought. I feel like Joe Marshallani was in before me, running late. Go ahead. What was your question?
So the right side would break in, there's
Nothing can flow in an open circuit. Let me finish this.
still voltage.
What? Say that?
There's still voltage.
Yes, yes. Think of this as an infinitesimal gap, right? All right. That's the idea. These gaps are so small we can't even think about it, but they'll stop the current from flowing. That's the idea. Now, if you have this, let me finish this thought here. How would you do it? Well, you got the current here, there, right? Hear me? Now, if I want the voltage on this one, what do? You just take this current times resistance, and I called it R2. And now you have what? The voltage across here, call it V2. Or call it VR2, right? Y'all hear me on this one? The final step is the easiest, and I want to make sure you see this. I need your attention on this one. This may be the problem, this kind of problem for the quiz. Hint. This may be the type of problem you get on your quiz. Does everybody hear me? I'll give you some more, don't worry, but watch. Now, if you look at this, what is this voltage going to be right here? Now, how much current is flowing? None, right? So if you start at the negative sign, if you want a voltage, how are you taught to do it? You know, the sum of the voltage drops around a closed loop is 0. But the easy way to do it is start at the negative terminal, go around here. You see you get an increase as V2 here, and keep going. What happens? You get an increase of VR2, right? And then you're over here. So that voltage right there is just the sum of that voltage plus the voltage developed there. You all see this, class? How many did? I'll give you some more problems. I'm sorry, I'm running late. I would like to have given it today, but I'm going to give it on Friday because I don't want to rush people on this one. All right, now, one more item I have. Everybody's packing up. No quiz, I'm out of here. Hey, does anybody know who we played basketball Friday? I know we lost to Baylor last night, unfortunately. You know?
Last time, well, I saw this one, but I did not stay on
All right. Now, I want to talk about something else. Yeah.
So, for the VEMF equals negative dVdt.
No, minus
minus the integral of
yes.
dVdt. So for the VEMF, that's the opposite of what we think of as regular voltage, right?
No, it's actually immeasurable voltage, but that is the voltage that's developed in a break in the wire.
Okay.
So you have to put a source in the wire that would create that voltage, which means the actual potential you put in there of the source is going to have the opposite signage, you might say. If you're going to get in other words, if you have this, just go with me on this one. Don't worry about the B field, but suppose I get plus to minus 10 volts there. All right, we know there's going to be a resistor there, right? Well, you don't put a plus minus 10 volt source here because current would go this way. What you would do is if you want to find something that replicates this behavior, you'll do this. You put a voltage source here that will be plus to minus 10 volts. Now, if you break that wire, it will get 10 volts. You all see that? And then you put your resistor in there. There's 10 volts across it. But if you just put a source of plus to minus 10 volts, current will go in the opposite direction. That's the idea. I'll give you some problems about this. I want to do one other thing. Now just listen. This is not hard to see. The problems I'm trying to show you are ones that are valuable to understand when you get into the real world, when you're doing EMC analysis. And you will probably have to do that at some level of EMC, electromagnetic compatibility analysis. You're going to get weird voltages. You've measured things. Have you all measured things? You have humming, there's noise, you don't know where it's coming from and how to deal with it. Well, 60 hertz is, might as well just mention this, everywhere. Right? Our wall output is 60 hertz, right? Anytime you get current flowing at 60 hertz, it causes magnetic fields to vary at 60 hertz. So when you have a small circuit, whatever, and you got a closed loop around a closed path, that voltage or that current will induce or create a B field that will induce a voltage that you can calculate. You can calculate these things very easily. And when you get close to that wall where the currents are flowing, it can be very large and can cause all sorts of problems. There's also the problem of if you have lightning. Lightning is a very large current event. It goes up to 20 kiloamps peak, or maybe 50 kiloamps. And there is something called a superbolt that can go to 270 kiloamps. My PhD had to deal a lot with this event. So that is a very fast rate of change of current that creates a very large magnetic field nearby where its strike point is. That magnetic field, if you have anything in the vicinity where you have closed paths for current to flow, in other words, standard PC boards and stuff like that, you get huge induced voltages unless you shield it properly. And that's what we talk about in electromagnetic compatibility. And most of the time, the product engineers, the last guy that takes care of all the problems that are unforeseen is this compliance engineer. They're very well paid because they have to make sure the product gets out the door. It's not vulnerable to EMI or EMC, and it meets the FCC, Federal Communications Commission's standards in this country. In Europe, it's CISPRI. And then if you work for the military, there's mil standards. But those guys are paid a small fortune, in my opinion, probably almost an order of magnitude more than the normal engineer, because they can make the product work in the field. And that's a big problem. I promise you it's a big problem. Just talk to people in business. Anybody here work at Dynetics or Adtran? Talk to your friends. Dynetics? All right. My brother's working for him right now, but they do some work with weapons too. But anyways, with radar, at Adtran, there's a guy named Joffe and Kevin Schneider's in charge. He's the chief technical officer up there, at least he was. These guys go bananas trying to get product out the door that won't be vulnerable to lightning, won't mess up. And they, when you design something, you all know this. In the ideal world, your design works perfect. It can't fail. Then you build the thing, especially high frequency. You don't know what in the world happened. I've had this experience many, many times. Orders of magnitude more times that things failed than they worked the first time. So I guess what I'm really trying to tell you is what you're about to learn about this is valuable in the real world. And if you get good at this kind of stuff, you will probably never be let go at a company. Because most people honestly don't. They have a hard time. I'm going to leave you alone. You guys can break it up now. And on Friday, we'll pick up first thing with the quiz. How's that?
So, is it going to be a different quiz?
Oh, I take it away. I tell you what, we'll do this on Friday, and I'm telling you what it's gonna be on, right? And I'm gonna say this, that, actually, let me take questions first related to the problems, then we'll get the quiz. But I'm trying to get it out of the way early.
So is this gonna be like a new quiz that we're taking today, or are we gonna have the same quiz